Okay, let's have a look. So, this is a good one to look at. Maybe we can look at a couple of these today. I was kind of hoping to do mean value theorem. Maybe if we have a little time at the end, maybe I'll just remind you guys about mean value theorem. It's a pretty simple one, but if not, we'll do that next week.
Daisy texted me to open the meeting.
Oh, yeah, whoops. Forgot to do that. Tell her it's open.
Okay.
Thank you. Okay. All right, something like this. So hot air balloon is rising straight up at a speed of 100 meters per minute. An observer standing 200 feet from the liftoff point. What is the rate of change of the angle of the observer's line of sight when the balloon is 600 meters high? Okay. So our picture then just would look like this. Does that make sense? Okay, now how do we label this? So with related rates, right, we want our snapshot. You guys have been doing a bunch of this. We want our snapshot values. We want to know what are the things that we know. You guys tell me real quick. Well, how would I label this drawing?
Base is 200 meters, that's a constant.
Okay, good. You ever get that? We want to write the base. You don't want to call that a variable. We want to write that as 200. Now the height, we just call like y or something, right? Because that is a variable, so that needs to be a y. And so what are our snapshot values then?
Y dot.
Okay, so y dot equals 100. There you go. Good. What else?
Y 600.
Y equals 600. And we're looking for theta dot. Okay, so we need a trig function. Well, we need something connecting theta and y. So what's that going to be? Tangent, right? Okay. So our parent function would just be tangent theta equals what, y over 200. Okay, so when you see problems like this is not essential, but you kind of want to set up the trig function so the ratio is easy to differentiate. Like what if, I'm going to take a break from this problem for a second. What if you were doing a problem, I just want to make a point. What if you were doing a problem like this? Different kind of problem. Like you had a problem where, for example, like Like, I think there was one on, I know we did one last year where kid's flying a kite and the kite is, has a constant height and it's moving horizontally in the wind, right? So say the constant height was something like 200 meters, and then this is x, and we're trying to find theta dot, same kind of problem, if we know how fast the kite's moving. Do everybody get what I'm saying? So the kite's like, our beautiful kite up here, it's going like that at some speed. When we set this one up, what's wrong with this? I mean, it's not like it's terrible. If I were doing this problem and I use this as my parent function, is there a better choice for a trig function? This will work, but differentiating the right side, you see that's kind of awkward? Because I've got a 200, I either have to use quotient rule or I have to use 200x to the minus 1. And so in my derivative then I'm going to get x's and x dots, right? You see my point? What would be a better trig function to use? Cotangent, yeah. If we use cotangent, that's just as easy a derivative, right? Cotangent is no harder than tangent to take a derivative of. And now on the right side, I've just got an x dot over 200. Okay, just a little, I want to make that point. Okay, so back to business. Okay, so we could differentiate then, both sides with respect to t, right? We'll implicitly differentiate it. What are we going to get on the left side if we differentiate? Secant squared. Theta. Theta dot. Equals what?
Y dot.
Okay. Y dot over 200. Okay, good. Okay, now what? So what are our options here? This is where we could either go back and we could solve for the initial value of theta, and that's okay to do, right? Because if we know that initially, well, during our snapshot, we know that we've got a triangle, and I'm just going to draw the triangle here. With these proportions, a right triangle with sides of length 200 and 600, right? And so I could easily find out what theta is. Theta is just going to be the arctangent of 3, right? (600 over 200). Agreed? Okay, we could do that. That's fine. And then I can just plug that in up here. But what I think is almost preferable is to use a reference triangle. Reference triangles are a great little trick on problem. You remember doing stuff like this? Have you done any problems yet on this assignment with reference triangles? This might be, I think there's only one or two. This is one of them. So with our reference triangle, we could just use Pythagorean theorem. And we know that this side is just going to be the square root of 200 squared plus 600 squared. What is that? We got. Say it again. Square root of 400,000. There we go. Okay. I don't know if that simplifies it. We'll just leave it like that. Square root of 400,000. Okay, and it's not a perfect square, I'm assuming, but I'm sure it'll simplify a little bit. We can do that later. So there's our reference triangle. Well, look, our answer, if we're solving for theta dot up here, theta dot is just y dot over 200 times the reciprocal of secant squared, which is what? Cosine squared, right? Everybody get that? Times cosine squared theta. Well, cosine squared theta is the same as cosine theta quantity squared, right? I mean, so we've got the ratio cosine in this case would just be 200 divided by the hypotenuse, and we're squaring it. So we get y dot, which was 100 over 200 times cosine squared is gonna be 200 squared, which is, what is that, 40,000 divided by the square root of 400,000 squared is 400,000. So we end up with, that just reduces to 1/10. So we just get 1/20th. And what would our units be?
Radians.
Radians per, what was it, minute, I think? Yeah, radians per minute. Does that make sense? Okay, that's a good, I like that one because of the reference triangle part. Okay, while we're on the subject, are any other related rates ones we want to go through? You guys got a chance to work on them? Any choices? Madeline, any choices? You got next dibs. I don't see Daisy in here.
Where'd you post the link?
It's in the, it should be just in the Google Classroom.
So there's a thing there.
What? Yeah, just go to the join. There's if she goes to Google Classroom, there's a join link there on the first page of our Google Classroom. Oh, hang on. It says not visible to students. What the heck? Something's changed here. Oh, here we go. There. Now it should work. They changed the format on me.
Did that?
Yeah. Huh? I love it.
Yeah.
Yeah, love it. Now that I got it working. Okay, what else? Andy, you got another one?
Not right now.
Sorry about that, Daisy. I thought it was visible, but they changed the format, and I didn't see that it wasn't visible to you. You got any, Madeline? Sure. Yeah, let's see, number 5. Oh, yeah, this is a good one, too. Okay. All right, so let's draw a picture. Here's our shoreline. Here's our shoreline. Here's our boat is going to be out here. There's our boat. Okay. So what can we do here? We can label constants. We know that 6 kilometers is a constant. We know that the beam is making an angle of 45 degrees with the shoreline. So here's our beam. There's our 45-degree angle, right? And it doesn't really matter which way we're assuming that this thing is sweeping out angle. And it doesn't matter which angle it is, by the way, right? It's going to be traveling the same speed along the shoreline, whether it's approaching the shoreline or leaving the shoreline. Okay, so let's just assume that this thing is moving this way. And we'll call this distance right here. Call that distance theta. Okay. So what do we know and what are we trying to find here? Oh, I guess let's see. What other variable do we need here that I didn't put up yet? This is one that's kind of tricky. If we're trying to, we have any ideas, if we're trying to know how fast the radar is moving along the shoreline, what dot would that have to be? That's a rate, obviously, right?
Theta.
No. Not theta.
Is it wherever the opposite side is?
Yeah, okay, so we could just call it like x or something, right? Like call this distance right here. If we call that x, does that make sense? The rate at which that's changing, wouldn't that be equivalent to the speed? Do you agree? Okay. So what do we know then? We know some stuff here. I mean, just by the geometry of the triangle, we know some stuff. What's x?
6. Yeah, 6.
It's got to be 6, doesn't it, right? Because this is 45, 45, 90, isn't it, right? So we know x is equal to 6. What's theta? Okay. And we know theta dot, or we can calculate theta dot. We'll do that. We'll calculate theta dot. And what are we trying to find?
X dot.
X dot. Okay, so it's making one revolution every 5 seconds. How are we going to come up with theta dot then? What units should theta dot have? Radians probably per second. Okay. If it's making one revolution in 5 seconds, this thing, that's what this board is. Not used to this pen. It's like really sensitive. One revolution's how many radians? 2 pi. Okay. Two pi over 5 radians per second then.
Makes sense.
I think I like that better. I don't really need the units. We'll just keep the units the same the whole time. Okay, so what's our relationship going to be then this time? It's a pretty similar problem, actually. We got to be able to relate thetas and x's here.
Tangent theta.
Yeah, that'd be tangent, wouldn't it? Right? Tangent theta equals x over 6. So differentiating, it looks almost like the same problem we had last time, isn't it? Okay, same deal. We can make a reference triangle. A reference triangle is pretty easy. 6, 6, 6 radical 2, right? And so we end up then with, and really, I mean, well, we even know what theta is. We don't even need a reference triangle, right? We can just do secant of 45 if we wanted. We can do it either way, it doesn't matter. Let's say we go this way. Theta dot equals cosine squared theta x dot over 6. Theta is 45, right? So cosine of 45. Is it okay for us in this case to mix radians and degrees? It's okay to feed a cosine function any kind of angle we want to because we're outputting a number, right?
Why don't you isolate the theta dot? I'm trying to find.
Oh, you're right. We're doing x dot, aren't we? Yeah, you're right. I shouldn't have. You are right. Okay, so we got x dot was, jeez, equals 6 secant squared. I'm going to write this as 6 theta dot over cosine squared theta. I can never remember what secant. I always think in terms of cosine anyway. So what is cosine of 45? Cosine 45.
Square root 2 over 2.
Square root 2 over 2. Good. So if I square that, I'm getting 2 over 4, so I'm getting 1/2, right? So I get a 1/2 on the bottom. And then theta dot we already know is 2 pi over 5. So what's that giving me then? I'm getting 24/5 pi. Is that right? Is that right? 24/5 pi radians. Oh no, I'm sorry, not radians. It's what are we measuring here? We're measuring kilometers per second. That's pretty fast. But it would be moving pretty fast. It's making a, I mean, that makes sense. It would be moving pretty fast. Okay? Double check that, make sure that's what they got. I can look at the solution. The answer. $15.08, does that seem about right?
Yeah, that's what it was.
Yeah. Okay. Okay. Anything else? Any more of those? Kind of enjoying doing some related rates problems. It's always a fun thing to do. Friday morning. Okay, if you haven't, I'll leave that question out there. I think I'm going to take a few minutes here. Go ahead and keep working. I'll take a few minutes and just remind you about mean value theorem. That'd be an easy thing to just review quickly today. Gosh, I don't even know. We can go pretty quick. Just take a look on the board real quick, and I'll just talk you through this. This is pretty minor league stuff. So you might remember this from last year, going through Raleigh's theorem and mean value theorem. So all Raleigh's theorem is, these are existence theorems. Raleigh's theorem nobody ever talks about because the mean value theorem just takes its place. But what's this saying? If we've got this function that's continuous and differentiable, continuous on the closed interval from A to B, and differentiable on the open interval, what's that? Do you remember what that tells us? If a function is continuous and differentiable? We had a word that we applied to that last year. Where is that? There it is. Oh, distance scales. What did I do here? This thing's changed. What the heck? Give me 1 second. Keep working. I'll tell you when I'm ready. I gotta fix something.
Unknown caller.
Whoops. Gosh, I might actually need to do that. Ah, there it is. Okay. All right. Okay, take a quick look up here again. I think I got it figured out. So what did we say from last year about something like this? Okay, never mind. What this thing's doing. Okay. All right, I think I finally got this. So when something is continuous and differentiable, you guys remember? What does this do? I don't even know what that thing is. What is this thing doing? Jeez. What is happening? I don't understand. Why is it working now? Okay. Okay, remember that's what we called smooth. If it's continuous and differentiable, it means I can put my pen down and draw it. If it's differentiable, it has no sharp corners, right? So if it's continuous and differentiable, it's a smooth function on this interval from A to B. So what does Raleigh's theorem say? Super easy. It just says that if f of A is equal to f of B and the function is smooth, then there has to be at least one number C in the interval for which the derivative is equal to 0. Think about that. Super simple. Right? It's just saying this. If that's A and that's B, and they're saying f of A is equal to f of B, it doesn't matter what kind of path. If it's a smooth path, then there has to be at least one place on that interval where we're going to have a horizontal tangent. Yep.
What time is it?
Thanks a lot, Kyle. I really appreciate that. That's great. Okay, that makes sense. And here's a little picture to illustrate our point. Maybe. There we go. Okay. Right? So all the mean value theorem does then is it just says, okay, well we're gonna tilt that. That's all it's saying is that if a function is smooth on an interval, then there's at least one number in the open interval where the slope of the tangent equals the slope of the secant connecting the endpoints, right? Remember we were looking at a picture of that last year, so here would be a picture, right? If this is A and that's B, f of A, or the point A, f of A, the point B, f of B, well then there's the slope, there's the secant line, the average rate of change over that interval. If the function is smooth, then there has to be at least one place where the instantaneous rate of change matches the average rate of change. Has to be, right? That's it, that's all it says. And then it'd be up to you to go find it, but that's it. It's just an existence theorem. Okay. All right, so see if you can't, I'm going to put up the mean value theorem, very short assignment on mean value theorem. See if you guys can't get ready, get through that stuff, related rates and mean value theorem. And then next week, what I want to do is I want to review the tables that we did. Remember the tables we did last year? Yeah, I want to, so like that'll be us on Tuesday, okay?
Can you request me if you're advisor today?
I can, yep. Anybody else? Good? Okay.
please press 2. For Dr. Carter, Dr. Rogers, Dr. Chung, and Ashley Christensen. Thanks, God. JS's Medical Center. This is Crystal. How can I help you?
Yeah, could I have Dr. Reddy's office, please?
This is Dr. Ray's office. How can I help you?
Yes, so I just got a reminder. I'm scheduled, I believe. Can I double check this and verify this? I think it's for Monday at 4.
Yes, hold on just 1 second.
Uh-huh. And if that's the case, I'm gonna have to reschedule.
Okay, what's your name, hon?
My name is Eric Oya, OJA.
Yes, you're at 4 o'clock.
Okay, gosh, I'm gonna have. Okay, so I've got another meeting at 4 that I cannot miss. So my schedule is so brutal right now. I'm a coach. I'm gonna have to reschedule. I'm gonna pull up my stuff here.
Okay. So Alita is here today, but she's with the patient. So what I'm going to do is I'm going to take her information now and let her know what's going on.
Okay, sure, thanks. First priority is probably just to tell her that I'm gonna have to cancel that one, and then reschedule. And should I just try to call back and get her later then, or am I able to reschedule with you?
I'm going to let her know. I'm going to cancel it now. I'm going to let her know, and she will call you back and reschedule.
Okay, perfect. That'll work. Awesome. Thank you so much. I appreciate it. Hello. Oh, that's all right. I just want to make sure. Yeah, I think we're done. I just want to make sure. Yeah. So I will look forward to her call. Thanks so much. I'll have a great day. Bye now.
Have any recycling?
I don't think just a tiny bit over here, but not a big deal. I'll transfer it over there for next time.
Perfect.
Thanks. Okay. Hey, Mitch. I didn't talk to him. Huh. Yeah, Zach was going to though, which was good. I encouraged him to. Uh, Well, he just said, I see your point of view, and uh, I guess I could, if we're gonna do it, I could see if I could, I'll see if Shaw wants to do it. And I said, well, I appreciate that. You know how I feel about this stuff, but really, I'm not really trying to suggest that somebody else should even do it. I feel like it's like this is just a I feel like this is just not good for our program right now. I mean, what's it going to look like? A, what happens if we get it and it hurts us, but what's it even look like if we go out and put ourselves in harm's way? And I mean, how's Mike going to feel about that? I feel like I said, I've been kind of running the scenarios here, and it seems like this just doesn't make sense. I mean, like, is the AD going to be upset with us for even doing this, given the current climate with over 300 cases a day? And well, it's okay. So here's what it was. I didn't even know what it was. It's the PYB thing. Well, no, I think it's just like a skills thing down there but yeah, I think it's at the convention center, I think, yeah. But I just said, I mean, and then he kind of said, yeah, maybe I'll just keep all the varsity out of it. I said, well, yeah, I think that's smart, but I mean, really, I don't think it's smart to have anybody down there. hmm I wonder if I should just go down and talk to Mike real quick and say, I talked with Zach, I've been thinking about this. Mm-hmm. Yeah, and what's that look like from a PR perspective? You know? Okay, I'm gonna go talk to him right now. I think that's, yeah. Okay, I'll let you know how it goes. All right, bye. Sure. Those work. I just want to make sure I'm not doing it day of a leave. I've got a mask on. I ran upstairs, so I'm breathing hard. Uh, okay, I got you on speaker here. Let me take a look. Um, gosh, where is this? Okay. All right. So you said Monday the 17th was.
Yeah, he's got that day. He's got some in the morning, starting at like 8:30 or 9, 10:30, 2:30 is the latest.
Okay. Does he have anything later on any other days, like in that vicinity? I'm a school teacher.
Oh,
I
I
teach.
see. Yeah, what's an ideal time?
Well, we get out of school at. Students are done at 3:35. And I mean, if you can't accommodate that, I understand. I just would rather not miss class if I could.
No, yeah, definitely. Okay, so let's see. We might be able to just push it out, a little bit further.
Sure.
Do you have anything late those days that week? No, but he's got like Monday the 24th. He's got a 4 o'clock. He's also got a 4 o'clock on the 25th.
We have a game on the 24th would work.
24th. Okay. Do you want to do like a 4 o'clock, 4:15?
I think 4 would be fine. I can make it over by 4.
Okay. Okay, so 4 o'clock on the 24th. Okay.
Perfect. There should be no conflicts there. That looks good.
Oh, good. Okay, sounds good.
All
You take care.
all right. Thank you very much. You too.
You're
Bye.
welcome.
Even more.
Morning.
Come on.
Hey, Troy.
Hey, what's up?
Not too much. It's been a Friday. Simple.
Yes. Okay.
This was your first period. Not much actually. It's just reviewing this. See you next period. You don't really have to do any assignments. Just oh, time to go. So, like moving stuff.
Oh, I miss her tenderness. Ew, that was ugly.
Hi, how are you?
Yes, sir. Where is Mr. Black? This- Why was he gonna just- She was just in his bum box. Just sitting there. She's gonna be covered in everything. I forgot that. I definitely done that in the room. Two numbers are empty. Where what's going zero?
All right. 30 seconds, not too bad, huh? Okay, here we go.
Let me get this back.
No, I was talking to one.
What?
One got a CDL, so I have to try to get the program anyway. Yeah, and I want to get them, he missed. Just get your high school.
Okay, get out your notes.
Oh yeah, Sierra will be here in like 10 minutes.
Okay.
She's finishing stuff up in Tom's house.
Oh, okay.
Whoa. That's a starting.
Yeah, I'll get them for you if you're missing them. Yeah.
Yeah. Yeah. You start.
Yeah, but it just depends who you work for. Because.
Whatever you do, don't work for Smith.
No, it's just because I.
Okay.
But he got his CDL, he's in China. No, he is.
Is it the cold?
Right. So we left off. Oh, let's see. Anybody else need notes? Okay.
Dang it, there's no lunch after this one.
I know.
Good thing my best friend always said,
This full day is kind of a rough go, isn't it?
Yeah, it's like,
Yes.
it feels so weird.
especially at the end at 6.
The classes
It feels really long too.
Yeah.
Yeah, it's even worse.
Okay, so we were going to look at, yesterday, remember, we looked at the impact that adding or subtracting h inside the function had, or adding or subtracting a number, call it k, outside of the function, right? And today we're going to look at what happens when we multiply a number out front by the function, coefficient. So this is the vertical dilation factor, okay? So I got another Desmos document cooked up for you here. So there's our regular parent graph absolute value function, just like yesterday. And now I'm going to turn on, that's P of x, right? Everybody see that? So everybody see that? There's P of x, absolute value of x. That's the green function. I'm going to graph, along with that, I'm going to graph f of x, which is a times the absolute value of x. But a right now is set at a value of 1, so it's not going to, it hasn't changed anything, right? How come that's, there we go. So there's the red function, which is identical to the green function. Okay, but now I want to know, you can make a prediction for me. What's going to happen if I change the value of a from 1 to 2? Okay, yeah, it is. It is. Watch what happens. It's the dilation factor, and what it's going to do is it's going to stretch the function vertically by a factor of 2. Now, I want you to look at the coordinates of those points. And let me do this one more time. I'm going to make a little change here, too. I'm going to go ahead and do this. I'm going to go in increments of 0.1. Yeah, we'll try that. There's 1. Now watch what happens if I drag this thing slowly up, drag A up to a value of 2. Look what's happening to all those points. Again, what are they doing?
Getting bigger.
Getting taller, aren't they? Right? Hey, Mike, I'm in class. Maybe I'll get back to you. Are you going to be around during lunch? Okay. Oh, yeah, that's great. That'll work. Yeah, perfect. All right. Bye. So take a look here. Look what this does. It takes like if we want to define the height of the function, that's kind of a weird concept, but just think about that for a second. If we're going to define the height of the function to mean how tall it is from its vertex, right? With our normal parent function, when we walk from our vertex 1 to the right, think about an ant walking on this thing, right? If he goes 1 to the right, he's going up by 1. So the height there, the function would be 1 unit tall when he's 1 to the right of the vertex. Does that make sense what I'm talking about? If he went, the height of the function, if he goes 2 to the right, well then he goes up 2. Height is 2. Okay? Give me 1 to 5 on that concept. I just make sure I explain that. Okay, everybody got that? Okay, so ask a question. That's so helpful to me if you guys could ask a question. I'll put you on the spot. Just try to. Right, so I'm talking about like the function is infinitely tall, isn't it? Right, but when I say the height of the function, I'm talking about the height of the function for specific x values.
So are you doing like rise over one?
I mean, kind of, but what I'm really saying is like, let me answer this question for me. If the ant started at the vertex, and if he were to walk along the function 3 to the right, how far up would he go? 3, wouldn't he? Right? Because the slope is 1. Everybody get that? Right? So give me 1 second. You guys talk, discuss that amongst yourselves.
Okay, so let's.
But what
You tell me. You made me hope that.
I don't know.
Oh, yeah.
He lied to do it. My mom's not for lying, but
I always can't.
she might go with it, but mom's doing it. I just talk to her about how. Because he told me to go see my because that's what he said. We need some values. And I can move you. No. For 6 months until we try. And I drove tonight, actually. So he's going, I'd be all right on pass. Try to do it. I'm gonna talk to Ron. It's been much. I'm gonna say I know.
I'm not sure.
get a better example for it, but I wanna do it before the end of the semester, so I might skip a week before school. To get my CDL. You have your CDL? You have to do a driver test. And they don't make you back to the stereo. I'm all right. It's just opposite, if you wanna go left, you gotta turn around. Yeah, but I didn't have phones or anything, so I might choke. That's what she was practice before we took the test. That's what Ron said, that I made you practice for it. Okay. That's practice trying to get it. I'm talking to Ron.
All right. Okay, where were we? We're talking heights of functions. Oh yeah. Okay, so look what this did. Now, the green function is the original function. So when we talk about the height of a function, I'm saying like if we go 1 to the right on an absolute value function, what happens? We go up 1, right? If we go over 2, we go up 2, right? It's really simple. Over 3, we go up 3. Over 4, we go up 4. So those are the heights. When I talk about the heights of the function, that's what I'm talking about.
It's not like rise over run.
Well, I mean, I see what you're saying. I know what you're thinking, and you're on the right track there. Exactly. Because the slope is 1,
Yeah.
we always go up as far as we go over for an absolute value function. Now, it'd be different for a parabola or something, right?
Yeah.
Okay, but for an absolute value function, we always go up as far as we go over. Okay, what I want to, the connection I want you guys to see here, though, is if the vertical dilation factor A is equal to 2, right? If it's equal to 2, then what does that do to the function? What does it do to the heights of the function?
Multiplies the x factor by 2?
It multiplies, well, okay, it multiplies the original heights by 2, right? So we could think of it this way. Now for the red dilated function, where we've multiplied our absolute value function by 2, look what happens. When we go over 2, we're going to go up 2 times 2. You see what I'm saying? Okay, when we go over 3, we go up 3 times 2. We go up to 6. We go over 4, we go up 4 times 2. You get the idea? Okay? So if I were to dial the dilation factor A, if I dial that back down to 1.5, then I'm just going to be multiplying my normal parent heights by 1.5, right? And so, for example, you make a prediction for me then. Where is this point right here? Where's this red point going to end up being? If I make A equal to 1.5, I'm going to go over 4 and up how far? I'm going to go up my normal amount, 4, times A, which is 1.5. What's 4 times 1.5? 6, yeah, right? We go up 6. So it should end up right there, shouldn't it? Right?
Yeah.
Okay, let's see if that happens. So if I dial A back to 1.5, hey, what do you know? It did. Right? Okay, everybody get that? Okay. Okay, what if A is 0.5? What's that going to do? What's it going to do? Okay, yeah, it's going to kind of squash it down, isn't it? Now the heights are only going to be 0.5 times or 1/2 times what they normally would be, right? So instead of going over 4 and up 4, I'm going to go over 4 and up 4 times 0.5, which is what?
6.
4 times 0.5.
6.
No, what's 0.5 times 4? What's 1/2 times 4?
Oh,
2. Okay, there we go, right? So if I pull this thing back down to 0.5, look what it did, right? I'm going to go over from the vertex. If an ant goes over 4 to the right, he's going to go up 4 times A, which is 0.5, so it's only going up 2. It squashes it down. Okay, everybody good? Give me 1 to 5 on that. Okay, oh, that's much better. Okay, we're getting there. We'll practice this a ton. Okay, so then multiplying by A. When A is let's say it's a positive number, bigger than 1, what did that do? Well, didn't that just stretch it by a factor of a? And when we say by a factor, factors are things that are multiplied, right? So we're multiplying the normal heights of the function by a to stretch it up, okay? If we multiplied by a positive number that was less than 1, like 0.5, what did that do? Well, it squashed it. It compressed it by a factor of a, okay? All right, now I want you to make another prediction for me here. Oh, you know what? I gotta